Hi, this is a two-part lesson on wave optics. In the first part of this lesson, we will talk about diffraction and interference patterns. All of the images that you see in this video are attributed to OpenStax College Physics, which is published by openstax.org and is distributed under the Creative Commons Attribution License version 4.0. In our last unit on ray optics or geometric optics, we talked about a phenomenon called dispersion. And dispersion occurs when white light passes through a prism. The white light gets separated into its separate colors. And the reason this happened is because refraction and the index of refraction, it turns out, is slightly dependent on the wavelength of light. So when white light passes through a prism, the violet component gets bent or refracted more than the red component. And this separates out the colors into a rainbow. Well, on this slide, you're seeing in the upper left, you're seeing a rainbow formed when white light reflects off the reflective surface of a CD. And down here, we see a bunch of rainbows when sunlight is viewed through a pair of glasses made of a special film called a diffraction grating. And in both of these cases, the color separation is a result of the wave nature of light and has nothing to do with dispersion. And that's what we're going to talk about, the wave nature of light in this lesson. The fundamental principle that we need to understand for thinking about light as a wave and how it behaves when we think of it as a wave is called the Huygens principle. And the Huygens principle basically states that as light propagates through space, we can think of the light as propagating along a wave front. Okay, so the black arrow represents the direction the wave is traveling, and the perpendicular line here is the wave front. So you can picture it as sort of the crests of ocean waves making their way towards shore. So the Huygens principle says if we want to know where that wave front is going to be at some point in the future, what we do is we can think of every point along the length of that wavefront as being a source of a new wave. And like dropping a rock in the ocean at a point, that wave will propagate out in all directions, like so. So every point along the wavefront is the source of a new wave. And at some point in the future, if we draw a tangent line to all of those little waves, we discover the location of the entire wavefront at that point in the future. So the reason this is important is we can think about what happens, like in this picture, when wavefronts come in to a place where there's an aperture where part of the wave will be blocked by some sort of screen. So what happens is the wavefront gets truncated, and the points that are at the edges of this truncated wavefront, according to Huygens' principle, spread out and fill in the space behind the obstruction, behind the aperture. And it turns out this phenomenon, this spreading out, is more dramatic the smaller the aperture is. And in general, this phenomenon, which is called diffraction, occurs when the size of the aperture, it's called d, is about the same size as the wavelength of light. And I should say that this phenomenon, diffraction, occurs for all waves. For example, sound waves passing through doors are diffracted and spread out and fill the space of the room behind the door. And this is why you can hear, one of the reasons that you can hear sounds emanating from an object even if they're not in your direct line of sight, because those sound waves will diffract around barriers and obstacles. So in the early 1800s, a physicist by the name of Thomas Young was doing an experiment. And in this experiment, he would shine light on two parallel slits that are pretty close together on an aperture. And if light behaved like a particle and you did this experiment, In other words, if light did not have a wave nature, and you did this experiment, what you'd expect to see on a downfield screen is two bright bars, one corresponding to light passing through each of the slits. But that's not what he saw. Instead, Thomas Young saw a whole sequence of bright and dark lines on the screen downfield. So what the heck was going on? The only way to explain what was happening was in terms of waves emanating from each of the slits, interfering constructively and destructively downfield on the screen to produce this pattern, this interference pattern of bright and dark lines. So Thomas Young and others were able to think about what's going on in terms of wave propagation in the Huygens principle. As the wavefronts of the light came into the slits, most of the wavefront got truncated, and the part that got through underwent diffraction and spread out behind the aperture. And in essence, what we have occurring here is we can think of each of the slits as being a source of a new wave, light wave, that spreads out in all directions. And the waves emanating from one of the slit going downfield can interfere with the waves coming from the other slit. And you get an interference pattern. This picture right here shows it more clearly, where this would be the location of one of the slits, and this would be the other slit. So as you go downfield, there's regions where the peaks of the waves coincide, like here, and there's regions where the minima of the waves coincide. So when you put a screen in front of these propagating waves, there's going to be certain spots along the length of the screen where peaks of one wave always coincide with valleys or minima of the other wave from the other source. And at those spots, you'll have destructive interference, which will give you dark bands in the interference pattern. On the other hand, there's regions where the peaks of the waves from one of the slits coincide with peaks from the wave from the other slit. And at those spots, you'll have bright spots because you have constructive interference. So the minima in the pattern are a result of destructive interference, and the maxima are the result of constructive interference. So what does the pattern look like? Well, you have a sequence of bright and dark bands that looks something like this, where there's a central maxima and these bright fringes that go off in either direction. These figures are trying to show what's going on in a more simplified fashion. So let's take a look at this part of the figure first. So in this part of the figure, what it's trying to show is when the waves emanate from the two slits, because the light that is from which these waves originate is from the same source, those waves are in phase with one another, which means at the slit, peaks will always line up with peaks and valleys will always line up with valleys. But what this picture shows is, because those slits are at different spots, the wave from the top slit, get my pen back, this wave travels a different distance, a shorter distance, to get to this spot on the screen compared to the wave from the bottom slit. So there's a path length difference which exists because the waves travel different distances to get to a specific spot on the screen. But it turns out in this particular example, the path length difference is exactly one wavelength, lambda. So if you have one wave and you shift it one wavelength relative to another wave, you will still have a situation where peaks are going to line up with peaks and valleys line up with valleys. So when the waves arrive at this spot on the screen, they're going to result in constructive interference because the path length difference is exactly one wavelength. So it turns out that this constructive interference, which corresponds to bright spots in the pattern, is going to occur anytime the path length difference, it's called path length difference, is equal to some integer multiple of the wavelength, where n equals 0, 1, 2, etc. Because if the path length difference is a multiple of the wavelength, you'll still have a situation where peaks line up with peaks and valleys line up with valleys. Well, what about the dark spots in the pattern? Well, at those spots, what you have is a situation where the wave from one of the slits traveled a different distance compared to the wave from the other slits, but the path length difference in this case is exactly half a wavelength. So if you have two waves and you shift one wave exactly half a wavelength relative to the other wave, what you'll have is a situation where the peaks of one of the waves lines up with the valleys of the other wave, and you'll have completely destructive interference, and this gives you a dark spot. So let's make this a little bit more quantitative. So in this figure down here, what we're seeing is that we're first making an approximation, and that approximation is that the screen where the interference pattern appears is much further away. Let's call that distance capital D, is much further away from the slits, or is sufficiently far away from the slits so that we can think of the path along which the waves from each slit travel to get to the same point on this screen as being parallel to one another. Now, in the real world, they can't actually be parallel. They need to be converging slightly. Otherwise, they'll never arrive at the same spot. But if the screen is sufficiently far away, we can assume that they're roughly parallel to one another. And under this assumption, we can quantify the path length difference, which in this picture is labeled delta L, of the waves from one of the slits compared to the other slit, S2 compared to S1, as delta L, and it's proportional to the angle that the path the wave travels along makes with the horizontal, which in this picture is labeled theta. Okay. In other words, the path length difference, the extra distance the light from S2 travels compared to S1, is delta L in this picture, and it's a function of the angle the path makes with the horizontal and the distance between the slits, which in this picture is little d. In other words, we have this little right triangle here, and delta L, the path length difference, is equal to d times the sine of this angle. And as we discussed earlier, a bright spot will result whenever this delta L, this path length difference, is a multiple, an integer multiple of the wavelength, lambda, where n is equal to 0, 1, 2, 3, etc. Now, let me change notation slightly to correspond with what's in your textbook. Instead of using n, let's use m to represent this number 0, 1, 2, or 3. And we put it all together, what we find is that bright spots occur in the pattern when m times lambda equals d, the slit spacing, times the sine of the angular position of the spot on the screen, theta, where m is 0, 1, 2, or 3. So when m equals 0, what we find is the position of that fringe is 0 degrees relative to the horizontal, which is exactly in the center of the pattern. So for two slit interference patterns, we'll always get a bright spot exactly in the middle of the pattern on the screen. And then we get higher order bright spots going out in both directions from the center. Now, what about the dark spots in the pattern? Where would their positions be? Where would their angular positions be? Their theta positions be relative to horizontal in the interference pattern? So recall from our previous discussion, the dark spots occur whenever the path length difference is such that a peak will line up with a valley. So if the path length difference is exactly half a wavelength, or exactly 3/2 a wavelength, or 5/2 a wavelength, you'll have destructive interference in a dark spot in the pattern. So in general, the dark spots will occur whenever the quantity m plus 1/2 times lambda equals d times sine theta, where m equals 0, 1, 2, or 3. Now I should point out that the first order, the m equals 1 bright spot and the m equals 1 dark spot, occurs on both sides of the central maximum. And your textbook represents this by saying that m can equal both positive and -1, positive and -2, etc. But I find that confusing. Just think that when m equals 0, we have the central bright spot right here. And there's an m equals 1 higher order maximum or bright spot on both sides of that central order maximum. So theta could be above or below the horizontal line in these pictures up here. So earlier I showed you a picture of a rainbow that was created by looking through at sunlight through a special pair of glasses. And I said those glasses were made of a diffraction grating. Well, a diffraction grating is nothing more than many slits that are equally spaced along a film. And this gives rise to an interference pattern that is very much like the two-slit interference pattern we just talked about. In fact, the bright spots in this slit can be described using the same equation that we just derived. Okay? And the difference is the patterns tend to be, the diffraction patterns created by a many-slit diffraction grating tend to be sharper, and the peaks in the pattern more localized than the peaks, the bright spots that are generated by a two-slit interference pattern. So how do you get a rainbow? Well, if you shine white light through a diffraction grating, the various color components have different lambdas. And since they have different lambdas, they're going to have different angular positions on the pattern. So the first order maximum for the violet component of the light is going to be closer to the central maximum than the first order maximum for the red component of the light. So the colors separate and you get a rainbow, except for the exact center of the pattern where all the colors still converge at the same spot, and you'll just have a central bright white spot in your pattern. So the two-slit and many-slit interference patterns that we just talked about can give rise to interference patterns on screens. It turns out that even if you have a single slit, a single aperture in a screen, you can still have interference patterns that are created on a downfield screen. And the reason this happens is because, according to the Huygens principle, the wavefront, as it passes through this aperture, every point along the wavefront can be thought of as a source for a new wave that then propagates out in all directions. And it turns out that those waves from those various sources, those various points along the length of the aperture, can interfere with each other as they travel downfield and arrive on a screen. So if you have a single slit, you can still have a diffraction pattern that looks very similar to the diffraction pattern of a double slit experiment. But the bright spots tend to be bigger and more spread out than in the double and many slit situation. We can learn where the dark spots the minima of these single slit diffraction patterns will be on a screen downfield from the slit by thinking about the wave in the same way we thought about the waves in the two and many slit case. In other words, the waves that originate from different points along the length of the slit are going to travel different lengths to get to the same spot on the screen. And we can consider the path length differences as giving rise to constructive or destructive interference. And with a little thought, and see your textbook for more details, we can derive an expression which allows us to find the location of the dark spots, the minima, the locations where maximum destructive interference occurs in the pattern, with a formula that looks very similar to the formula that gave us the locations of the bright spots, the maxima, in the two slit and many slit situation from the previous slides. M lambda equals D sine theta, where in this case, M can't be 0, but it can be 1, 2, 3, etc. So although this equation looks very similar, there's a very important and significant difference between this equation giving the dark spots of a single slit pattern and the equation from the previous slides, which gives the locations of the bright spots in the two or many slit pattern. And that difference is here, big D is the width of the slit, whereas previously little d was the spacing between the slits. So when it comes to single slit diffraction patterns, we have an equation, this equation, that allows us to find the locations of the dark spots, the minima in the pattern. But there is not an equation that can easily be written down to tell us the locations of the bright spots in the pattern. So we're almost done with this mini lesson, but before we end, I want to back up to the slide where we showed the Young's double slit experiment and the interference pattern that results when you shine red laser light through two parallel slits that are close together. And what we saw is you get a double slit interference pattern where these bright bands appear on the screen. But if you look closely, you can also see a single slit diffraction pattern on the same screen, because the two individual slits which give rise to this interference pattern individually are single slits and create a diffraction pattern where there's a bright central maximum and these higher order bright spots punctuated by these dark bands in between. So what we see is in the Young double slit experiment, we have a two slit interference pattern superimposed on a one slit diffraction pattern. Both patterns are there simultaneously. So this concludes this lesson. In the next lesson, we'll talk about other consequences of the wave nature of light and diffraction.